Yeah, so we are happy to have Joel who tells about tropical wavefronts and nodal tangles.
Thank you. Well, today I want to talk about, what is on the title slide. So here's the setup. I want to talk about compact toric symplectic four manifolds. And so here, there we have like our manifold XW, and then mu is a fibration onto some delta, which is a Deleuze polygon. It's a subset of R2. And this gives us the toric structure. And the interesting thing is about toric symplectic four manifolds is that thanks to So first a bit about the structure. So here it looks like this. So our delta is the polygon. So, and like if we have a point in the middle here, then a fiber over this point will be a torus, hence the name toric. Also, if we take a point on the boundary, then it's just a circle, and if we take a point in a corner, then it's just a point in the manifold XW. So, okay, that's the structure of this fibration. The nice thing about toric symplectic manifolds is there's Deleuze's theorem, which tells us that the Deleuze polygon is enough to determine the symplectic manifold XW omega and the fibration mu up to some equivalence. But so this is nice because we can study symplectic manifolds by just studying these Deleuze polygons, which are subsets of R2. So given that, we might ask ourselves, well, delta determines the symplectic manifold and the toric action. Can we also just tell what the symplectic manifold is without like throwing the information about the toric action away? And like if you have, so you might have two different Deleuze polygons and you want to know, do they represent the same symplectic manifold? And well, historically, there's been some progress on this. So that like in the 90s, McDuff showed that the classes so we're still talking about compact symplectic four manifolds. So here she showed that X omega is either S2 cross S2 or some blow up of CP2. So this limits what you need to study. And then like in 2014, Yerkashon and I forgot his first name, Kessler, showed that the symplectic forms on these blowups of n-fold blowups of CP2 can be determined by some reduced vector. And this reduced vector, this is just some vector in n plus 1, where like n is the number of blowups of CP2 I took. So this gives us some kind of description on how we should try to classify these symplectic manifolds, which we want to represent. And indeed, you might say, okay, well, if I have a Deleuze polygon, you might know this, you might not know it, but you can calculate the homology of the manifold together with the area class of your symplectic form. And this is enough to determine this reduced vector. Though you have to do some combinatoric stuff, but modulo this combinatoric stuff, this is more or less a solved problem. So, okay, I've answered the first question. Let's go on to the second one. The second question is, like, if I have two different toric fibrations on the same thing, can we connect them in some moduli space? I've heard moduli spaces are trendy, so let's try to do that. And Also here, there's also some suggestion by Symington, which was in the form of a conjecture in 2003. This should be possible using almost toric fibrations. So, okay, I told you what toric manifolds are and toric fibrations. I'll give you a short crash course on almost toric fibrations so that you can understand what this conjecture means. So an almost toric fibration is, as before, like a map from a symplectic manifold to some base B. The base B, here's a picture. It looks almost the same as in the toric picture. You still have these 3 types of fibers, but you get an additional type of fiber, which is represented by these crosses. These are called nodes. And here what you have is you don't have a torus as a fiber, but you have a torus where you replace like one generator in, like you collapse one generator in this first homology to a point, and then you get this sort of pinched torus or Whitney sphere where it's a sphere with 2 points identified. So that's more or less how almost toric fibrations look. And the base has a special structure near these nodes. So you notice that I drew like a dotted line which always goes into the nodes. And this is because usually if you have a toric fibration, in the interior, your fibration here is flat. So there you have a flat space. But near these nodes, there are like a cone point. So you can imagine it like a cone point. So there it's not flat. There you have some non-smooth point of the base. And this non-smoothness is, well, so if you have this cone and you wanted to draw it in a flat way, well, you have to cut along somewhere. And this dotted line is to denote where I cut the base. And in particular, this cut is in such a way that, so if I draw a straight line in this base, it looks like a straight line, all right? But if I go through this cut, because there I have cut my flat structure, so here the straight line will be diverted like this. So I get straight lines which look as though they're bending when they're going through these cuts. And okay, why is this a good candidate for a moduli space? So we have 2 operations on these almost toric fibrations we can do. One is the nodal trade, which is every time in a Del-Sand polytope where we see a corner like this, so here's a local picture of it, we can make a nodal trade, which means we replace the corner by some node like this. And then you might say, okay, the boundary here, it still has a corner here. But actually, no, because remember that like straight lines, when they're going through the cut, they appear to be bent. And the same is happening here. So if I draw a straight line that is parallel to this boundary here, then when it's going through this cut, it will be bent. So the boundary is actually a straight line. And so it bends around this corner. Okay, so this is the nodal trade. So this is the nodal trade, and there's a second operation, which is nodal slide. So when I have a node, I can modify my fibration by moving a node back and forth along this cut line. So for every node, I have a 1-parameter choice on where I need to put it. And all these modifications in the base I can represent by some varying parameter t of my fibration, where I have also a varying base, but I keep the manifold on the top the same. So I have a varying fibration, the manifold stays the same. So, okay, back to the question by Symington. How can we connect two Del-Zand polygons with each other with almost toric fibrations? Well, here at each corner we can do nodal trades, which means we can like put like little nodes in there. So we do that. And then once we've done that, for every node, we can slide them along their lines. So for example, this blue node, I could slide along this red line back and forth. And this pink node, I can slide along this line back and forth. And then I can try to slide these nodes back and forth a bit. And then at some point, they go back into the boundary to give some other polytope. So here I'm starting with the polytope I have drawn on the left here on top. So this is my delta 1. And then I modify the fibration by doing all these nodal slides and stuff. Then the node slide back into the boundary and I get my delta 2. And so I have this sort of braid that connects these two things. So that's the goal. So the goal is, if I have two base diagrams of the same manifold, I want to find this braid that connects them. But this is not obvious how you should do it, because like there's, yeah. So maybe it's better to just take a break for now at the private swimming pool all mathematicians have. And then, well, you relax a bit and then you notice maybe there's been an earthquake or something. So there's like wavefronts propagating from the edges of the pool into the middle. And, well, you're a mathematician, so you think about how you could describe this mathematically. So if you have some pool which is given by a polytope, which, I mean, spoiler, we want to talk about polytopes later. So, and the polytope has some boundaries, and then, well, if you have some edge, there will be a wavefront propagating from it that is parallel to the boundary, and then for every boundary component, you have like this wavefront which is coming in. And then you have, for every boundary component, you have this wavefront, and then you just take the intersection of his wavefront, so the area here in the center. And that the boundary of that gives you the wavefront. Okay, so how can we write that down a bit neater? So our polygon is given by some equations. So here we have some lambda I, those are the normal vectors of the boundary lines. And they're given by some linear equation like this. And then, so we take all the, so this gives me everyone defines me a half plane, and then I take the intersection of all these half planes. I can also write it as just taking the minimum of all these linear functionals and then checking that it's bigger than 0. So that's a way to describe my domain. Also, to make it unique, what I'm about to do, we should choose some normalization for this delta I. So here I'm choosing delta I to be in S1. So everyone should be a unit vector. And then we can define the propagation of the wavefronts is just we replace the 0 here by some t. And that makes such that every of these half planes advances into the direction of the normal vector. And then we get these concentric wavefronts that go into the middle. Here, this minimum of all these functionals, we can will use it more often, so I just define it as f of x. And so these red areas here, the interior is given as the pre-image of all values greater than t of this function. Okay, but now our break wasn't happening at a normal swimming pool, it was happening at a tropical swimming pool. And tropical not in a geographical sense, but like a mathematical sense. So this means our normalization we choose should be a bit weird, in a tropical sense normal. We should take our normal vectors to be in Z2 such that they're primitive vectors, so that there's no shorter vector in Z2 pointing in the same direction. And other than that, we take exactly the same setup. It's just now the normalization of all these normal vectors is a bit different. So here's a picture how that looks for some Delzant polytope, which we will be interested in. And now there's some special set here, namely it's the caustic. The caustic are all the points where this function f, the minimum of this function f is realized more than once. So for example, here at this point, there's the minimum of this edge and the minimum of this edge, which give me the same value. So that's the point of the caustic. And then we have like this line, which, yeah, that's the caustic. Actually, this is a tropical curve if you are interested and to know what that is. But today, it will be fine if we don't know what that is. So there was a paper 2 years ago by Mikhalkin and Shkolnikov, and they showed that this caustic K has some very particular structure up to GL2Z transformations. Namely, if we take some vertex, which is not in the maximum set of our f, so f attains the maximum along this line here. So if we take a vertex which is not in there, so like this or like this one or this one, then it will always look like this. Up to a transformation by a GL2Z matrix. And if I have a vertex which is in the maximum set, then it's a bit more complicated, but I still have this finite list of things which it can be. So I have these 1, 2, 3, 4, 5 things where the maximum is just a point. And then if the maximum is a line, like in this example here, then I can have 2 vertices in the maximum set. And in this case, the vertices look like one of these two. So here this vertex is an example of the 6, and here this vertex is an example of the 7. Yes. So now we have this caustic. We know a bit how it is behaved. So now we have some guidance on how we can construct this braid for our almost toric vibration. So it works like this. So you start with some corner here. There you can do a nodal trade. Oh, wait. There you can do a nodal trade. So here's a node, and you can put it into the middle somewhere. So notice that first it goes along the caustic, and then at some point it goes off, like falls off the caustic. All right. But now if I start with this in this corner here and do the same thing, remember nodes slide in straight lines, but also straight lines, if I go through a cut like this, they become broken lines. So if I slide a node through here, it goes around the corner. And the effect is that it slides exactly along the caustic, which is magical, or like it's a coincidence, but it's a very helpful coincidence. And the good thing is we have the standard model for all these corners here. So at every corner, the same will happen. So what we do now is we do this. So we slide a node up, and then we slide the next node through. And then we proceed with the next thing until it falls off. And then the next one will again follow the caustic. And then here we can do the same thing. Here I put these two nodes at the same time, and then the one that is left over, this will make a zigzag path through there. It will also follow the caustic. This is just because, like, at every vertex I have the standard form, so I can study it in the local model, and there I know what will happen. And here, the rest I just slide up until they reach this maximum set. So then we get a picture like this. And here, so we have these nodes in the maximum set. This maximum set and its neighborhood I call the hat of the polytope, because, I mean, it's on the top, so it's the hat. And the other nodes, they're parked nodes, because at some point they didn't have, like, wanted to go on. Yeah, so, and here's a schematic view of this picture. So you can notice, if you try to draw like the path at which these nodes should slide, then you see that they always slide parallel to the boundary. And in fact, so they slide in circles. So if I just do a schematic view of what is going on, I have these parked nodes, which are here in blue. They slide in circles. The boundary, remember the boundary, because I did all the nodal traits, the boundary is a straight line. So here I've drawn it as a circle, but the boundary has no corners in it. And I have these parked nodes, and they slide parallel to it. And then I have these nodes in the middle. There are the hat nodes. They just sit in the middle. Okay, what I can do with this now is, the thing is, if I have in an almost toric manifold, if I'm in a situation where I have something like this, I have some node which slides parallel to the boundary, or whose cut is parallel to the boundary, then I can always do a what's called a almost toric blowdown, which sort of, for our purposes, it just erases the node by doing a blowdown on the corresponding manifold. So what we can do is we can do almost toric blowdowns for all these blue parked nodes. This leaves us in a situation where we just see the hat nodes in the middle. But remember, like, the hat nodes are also classified on how they can be arranged. So here we find ourselves in, well, in this case, it's like 9 different cases how the hat can look. And then for each case of the hat, we can do some more blowdowns. And then we can always go back to CP2. With some symplectic form omega. And okay, so here we started with the original manifold X omega. We did some blowdowns of sizes delta n till delta k and delta k plus 1 and delta 1, and we arrive at some CP2 of size lambda. And it happens that these deltas that we obtain, they exactly give this reduced vector lambda delta 1 up until delta n that determines the symplectic form on our manifold X. So that's very nice. So we found a second answer to our first question. We just arrange our base diagram such that it has this canonical form. And from there, we can read off this vector. And it's even better, like this reduced vector here, it also determines the symplectic form. So here we have a one-to-one correspondence between this reduced vector and it determines the symplectic form, but also it determines this canonical form. So here we have a one-to-one correspondence between this vector and the canonical form. So, okay, this gives us this answer to question 1. If we want to know what the reduced vector is, that is, corresponds to some Delsan polytope, we can just do these nodal slides such that we arrive at the canonical form, and then we can read off the reduced vector. So here, the sizes of the symplectic blowdowns, they're given by the distance of this parallel sliding node to the boundary. So here the size would be delta if like this was the height delta. So from this, just from the geometry of the base, we can read off what the symplectic manifold should be. And we also found an answer to question 2. Because of this one-to-one correspondence and that the reduced vector uniquely determines the symplectic form, we also know that the canonical form is unique for some given x omega. So to connect two different base diagrams, we can just connect them to the canonical form. The canonical form will be the same thing. So we have constructed a braid that connects two base diagrams. So yeah, we've answered both our questions. So that makes me happy. I hope you're happy. And I'm also happy to answer any questions you might have.
Okay, thank you, Joe. Are there any questions?
Hi, Joe. Can you draw for us how these how do you see the canonical form for, say, S1 cross S1 with certain size and an even dynamic Hilbert surface, and then as an example, and how to recover the amount of tangles that you want to go from one to the other?
So, okay, maybe I'll not do S2 cross S2, because S2 cross S2 is always a special case, but I'll do the 1-point blow-up of CP2. So, in this case, the canonical form is really very simple. Like, the canonical form is just so you put these nodes in the middle, and so in this case you have no parked nodes. So in the first step here, in this step here, you have nothing to do. You don't have to do any almost toric blowdowns. It's just working out these toric blowdowns that you need to do. And here, I mean, there it's a bit different for every case. But here, you just undo what you did. So you put the node back into the corners. And then you can, wait. You put the nodes back into the corners. And then you can do this toric blowdown here. So in this case, nothing really happens. So a case where this would be different is if I have a base diagram which looks like this. So I take some, let's take some small blow up of CP2. So here I will get a parked node. So let me this time do the colors properly. So I have, this gives me a parked node, and then I have these 3 nodes which meet in the middle. So this time this hat corresponds to the first thing here in our list. So here what I'm doing there is I'll do a almost toric blow up, blow down along this node here. So this means here I'm inserting like a little triangle here. And then I go back to, and then I see that I'm already back at CP2. So, yeah. So here it would be like this blue node is here, and then I cut out this triangle here from this base diagram. And then through some redrawing of the base diagram, I get to the one on the left. Is that what you wanted, or?
Well, not quite. I was like more thinking on taking, for instance, if you take a Riesenberg surface of degree 2 and the standard toric thing, well, we know that we can do like just one mutation and go back to the standard P1 times P1 with some sort of symplectic form, and then this is true for all even dimension Riesenberg surface. They are all P1 times P1 with some other symplectic form. And then what I wanted to see is that how you go from the Riesenberg one to the to your standard model, that probably you should get a rectangle as the hat. You would put the nodes there, and how you would know what type of mutations you would have to get to recover the correct the toric structure on P1 times P1.
Yes. Okay. So first of all, I have to admit to a lie, since you asked a good question. So here, when I'm talking about that the reduced vector uniquely determines the canonical form, it uniquely determines the canonical form up to some nodal slides. So like the reduced vector doesn't determine where these parked nodes will be on their orbit around the center. Also, the reduced vector only determines the hat here up to some moving around of the nodes. So what happens if I'm in the case of the Hirzebruch surface? So it looks something like this, maybe. Then, like, I'll be in the situation where I have a hat like this. No. Like this and like this. So the maximum of the function will be this line segment here. And now if I want to go to the standard S2 cross S2 picture, what I'm doing is I'm just modifying the hat of the thing. So I'm just modifying a small neighborhood of, like a small neighborhood of these nodes here. And what I'm doing is I'm doing a nodal slide with So I'm leaving this alone, and I'm doing a nodal slide with, let's choose the right colors, with this one. So this slides a bit down here, and this one stays where it is. And then I have to do this change of branch cut business. And then I'll get to the standard S2 cross S2 picture.
Okay.
Yeah.
Right. Okay, so this was already encoded inside the hat, and you have
yes. So
you know how to represent the hat in the end. That will.
Yeah. So the hat is, you should look at it as some equivalence class where you can move the nodes inside the hat around.
Okay. Okay. All right. So it's okay. I think I'm fine. Thank you.
Good. Any other questions? Yeah.
Okay, I'm gonna ask it here directly so that we don't have interference. So, the initial question that we were asking is to see how we can extract the symplectic data, so how we can extract the data on the total space based on the Dalzon polytope, so based on our moment image, right?
Mm-hmm.
Okay. And my question is, don't we already know this fact from the, like, I'm not sure how much of an answer we get from the Dalzon uniqueness theorem.
Yeah. Like as I mentioned at the start, like there's all the work that was done previously on this. Like you totally can get an answer on this question. Like we have with the work of McDuff and Harshon and Kessler.
Yeah.
You have all the ingredients you need. It's just that from the base diagram, you can read off the homology of the base, and then you can determine the sizes of the symplectic spheres you see from that.
Mm-hmm.
But those sizes, they're probably not all -1 spheres, so they're not all correspondent to the deltas of your blowdowns. So you need to do some change of basis in your homology to actually read off these lambdas. And to me, it's not very clear how you would achieve, like, how you would systematically achieve this. I'm sure there's some way. I mean, you can probably construct a way with like this canonical form as well. But like if you just have the homology and you need to do some change of basis there, it's not that easy.
Okay, easy. But if then my confusion is at the fact that, so according to the Dalzon uniqueness theorem, we know that two total spaces of such a fibration would be equivalent up to fibered symplectomorphism.
Yeah.
So the question is, what level of what rigidity are we?
So here I was interested in not in just symplectomorphic. Like I have two. There are some polygons. I want to know if the spaces that are above it are symplectomorphic, not fibered symplectomorphic.
Okay, I see. All right. Thank you very much.
No problem.
Okay, so thank you, Joel. Thank you, Alain.